So we're now going to move on to taking a look at other types of graphs, and we're going to make some predictions first. So this next little section, go ahead and title Making Predictions. Sketch yourself 4 sets of x and y axes. And then the first one I'm going to talk about is the linear function. So with the linear function, we know it's just a line, and I drew a positive slope line. And with a linear function, we have in the equation, I know the standard is y equals mx plus b. But what I want you to get here is that there's only one x in the entire equation. And then in a quadratic, or the parabola we just talked about, we have an x squared. So I want to take a look at the next 2 types of functions and see if we can make some predictions based on those. So the next would be a cubic. And that function would mean there's an x cubed, hence the word cubic. And that would look like this, like a little squiggle. And then the next function would be a quartic. And that's for x to the 4th power. And that looks like a squiggly W. So here's the prediction I want you to see, or that I want you to make. So in a linear, there's one possible x-intercept. In a quadratic, there's 2 possible x-intercepts. In a cubic, there's 3 possible x-intercepts. In a quartic, there's 4 possible x-intercepts. Where do we get the possible from? Take a look at the exponents. Linear would be x to the 1st power. Quadratic is x to the 2nd power. Cubic is x to the 3rd power. And quartic is x to the 4th power. So the big takeaway here is that the exponent equals the number of possible x-intercepts. And you'll see that pattern as we get into bigger functions. So again, make sure you have this all copied down. So the next thing I want to talk about is a cubic function. A cubic function has a standard form of f of x equals ax cubed, so to the power of 3, plus bx squared plus cx plus d. And the big difference with the cubic function here is it changes directions twice. So on the one on the left, it goes down, up, and then down. There's maximum and minimum points. And in a cubic function, it keeps going left and it keeps going right. The first graph on the left would have a positive a value. And the second graph on the right would have a negative a value. So just like in a quadratic, that first coefficient, or number out front, controls how the graph is shaped. And here's what my notes look like. I did cover my pictures back up because I'm going to add some things to them. And now we're getting into definitions that meet our goal, so I would write these in red. So the first definition is a relative maximum. So a relative maximum is where a function changes from increasing to decreasing. And you saw that on a quadratic where it went up and then down. That was a maximum point. A relative maximum, I'm going to call it a peak in the graph, or a mountain or a hill, whatever you prefer. A relative minimum is where the graph changes from decreasing to increasing. And again, we saw that in a quadratic when the minimum value was at the bottom. For minimums, I'm going to refer to those as valleys. And here's why I covered up my pictures. So in a cubic, you're going to have both. You're going to have a relative minimum and a relative maximum. So the relative minimum is this lowest point here, and the relative maximum is the highest point on both set of those pictures. And if you don't have space to label them, that's fine. Absolute maximum is where the function obtains its greatest possible value. And you will see that in the two examples that we're going to do. So a relative maximum is a high point, but it's not the highest point, where an absolute maximum is the highest value. The opposite of that would be an absolute minimum. And that's where a function obtains its smallest possible value. There you go. And again, a relative minimum is a minimum point. It's just not the absolute lowest point. So make sure you have all those notes written down and those definitions in red.